Morning in München and good afternoon in Taiwan. Today is really my great pleasure to welcome Tobias Böhle from Technische Universität München from Germany. And he will present his recent research about bifurcation analysis of so-called twisted states in phase oscillator network. And I think he will tell us about a very beautiful story about Kuramoto model, and there's a big network, and there are so many interesting phenomena, synchronization, chimera maybe, and really we are very curious about his talk. So let's welcome him.
Yes, so thank you very much for the very nice introduction and also the opportunity to speak here. So yeah, today I want to report about a project that I did in collaboration with my two PhD supervisors, which are Christian Wick, who is from Amsterdam, and Christian Kühn, who is also from Munich, where I'm also based. So let me start with a very brief introduction of phase oscillator networks. So an oscillator is basically everything that has some kind of periodic or repeating motion. For example, in the heart, or more generally here in the sinoatrial node, there are many cells that determine the rhythm of the heart. So that's some kind of repeating motion. Also in the global power grid, the current changes its direction with a frequency of 50 Hertz, or at least that's the frequency in Europe. I'm not sure about the Taiwanese power grid, but yeah, it also changes its direction multiple times a second. So you can consider this as an oscillator. And yeah, the power grid is made up of multiple households, transformers, power plants, and so on, and they are all connected with each other via these electrical power lines. Okay, and if you describe an oscillator just by its phase, so just by a value on the unit circle between 0 and 2 pi, then you also call this oscillator a phase oscillator. And if there's some non-trivial coupling structure, then you have a phase oscillator network. The prototypical mathematical model that describes these phase oscillator networks is the Kuramoto model that's given in the box right here. So the Kuramoto model describes capital M coupled oscillators that are described by the phases phi I. So phi I is the phase of oscillator I. And then in the Kuramoto model, the time derivative of the phase of oscillator I is equal to omega I, that is an intrinsic frequency of oscillator I. So this is just a real number. And then you add the coupling strength K over the amount of oscillators M, and then you sum J from 1 to M, and then overall Aij times sine of phi j minus phi I. And here the sine, this is just a coupling function. And Aij, these are coefficients that you can regard as entries of an adjacency matrix of a graph that describes the coupling structure. So that describes which oscillator is coupled with which other. Okay. So now we want to consider a very specific case of the Kuramoto model on graphs. And in particular, we consider this case. This is special because here there are no intrinsic frequencies. So we have all set them to 0. And if there are no intrinsic frequencies, then you can also rescale time such that the coupling strength is equal to 1. So this is why there's no coupling strength here, but just a 1. And then one more fact that is specific here is that the coefficients of the adjacency matrix only depend on the difference I minus j and not on I and j separately. And in particular, we want that these coefficients a I minus j or a l are defined to be 1 if the minimum of the absolute value of L and m minus L is less or equal than k and 0 else. And k is just a real number. Yeah, and if you define the coefficients in that way, then you obtain the adjacency matrix of k nearest neighbor graph. So for example, this picture here, this depicts a 5 nearest neighbor graph on 20 nodes. So yeah, you can see that there are 20 nodes and k is equal to 5, which means every oscillator, so say the first one is coupled to 5 oscillators to the right. So 1 is coupled to 2, 3, 4, 5, and also to 6. Yeah, and then the oscillator is also coupled to k oscillators to the left. So yeah, that's why in this example k would be 5. Okay, and then if you consider this specific Kuramoto model with this specific choice of the coefficients, then it turns out that there are very interesting equilibria. And in fact, they are called Q-twisted states. So for every natural number Q, well, you can even say for all integers Q, but let's just focus on natural numbers. Yeah, for each natural number Q, a Q-twisted state is given by this formula here. So then the ith oscillator has phase 2 pi qi over m, and then you can add a possible phase shift alpha if you want. So this figure illustrates a 3-twisted state here. Yeah, where Q is equal to 3.
And Tobias, can I ask
yeah.
a question? So
yes,
why
please.
do you call this state twisted? This is my first question. And the phi iq is independent of k. That's a little bit surprising to me. So
what is independent of k?
Yeah, and also why is this called twisted? Twisted, why?
Okay, so I think it is called twisted because it twists around the circle.
Okay.
So here on the y-axis, on the vertical axis, this also represents the circle that basically starts from 0 and ends at 2 pi. So these states kind of wrap 3 times around the circle, or maybe you can say they twist around the circle.
I see.
Yeah, I would say that's why they are called twisted.
Okay.
But I didn't get the second part of the question. What is independent of k?
I mean, so you consider k nearest neighbor graphs, but in the formula of the Q twisted state, there's no k. K does not play any role.
Oh yes, that's right. So for any k, these are equilibria. Yes.
I see. Interesting. Thank you. Yeah.
Yes. Yeah.
Tobias, if I may, this alpha phase shift is anything, right? Because the difference essentially makes it vanish.
Yes, exactly. But so, alpha has to be independent of the oscillator I.
I see. So are we talking about actually lines of equilibria rather than just equilibria?
Yes, exactly. So there's a one-dimensional continuum of equilibria. Yes.
Thank you very much.
Yes, you're welcome. Okay, more questions?
Of course, I can ask, why do you consider this special graph? There's many symmetry, I know. And
yes.
Because here we have an expert also in Kuramoto called Chen Shixin. He considered 2 nearest neighbors or 1 nearest, just the neighbors. But now you consider more, you consider k nearest. And what is the main reason or applications? I'm asking about why do you study the k nearest neighbor graphs? Yes.
I'm not so sure about applications. I think there are some applications of these nearest neighbor graphs in neuroscience, but I have to admit that I'm not an expert on that.
Thank you.
Okay, then I can maybe continue. So if you have a dynamical system and you have an equilibria, so these are all equilibria, then the natural next step is that you want to look at the stability of these equilibria. But it turns out that calculating the stability of these equilibria is not that easy. And so what one usually does is one considers the continuum limit as m goes to infinity. So that's what we do next. So we want to consider a graph sequence, but yeah, first we fix a parameter r in the interval from 0 to 1/2. And then we consider a sequence of r times m nearest neighbor graphs. We multiply r times m, and then we take k as the biggest integer that is below r times m. And that then produces a sequence of graphs that's illustrated in this series here. So for example, if r is equal to 0.2, you can start with a 2 nearest neighbor graph on 10 nodes. Then you transition to a 4 nearest neighbor graphs on 20 nodes, and 8 nearest neighbor graphs on 40 nodes, and so on. And then in the limit only the ratio between the two, which is r equal to 0.2, that's the only thing that's crucial in the limit. Yeah, so on each of these graphs, you have your own Kuramoto model, which is this one here. And I have added an additional index m everywhere here to make clear that it in fact depends on m. Yeah, and then you can send m to infinity. So consider the continuum limit and then in this continuum limit, the position of the oscillators is now given by a function theta, and the oscillators are now parameterized by a continuous variable x, from where x is basically from the unit interval, but we have also identified 0 with 1 so that we can keep the ring topology, and that makes the notation a bit more easy. Okay, so to transition to this continuum limit, basically what you do is you replace the averaging sum with an integral here. The sign coupling function remains exactly the same, and these coefficients they get replaced by a graphon. Yeah, so usually, as I said, these coefficients depend on I and j separately. Then you get a graph on W here that depends on X and Y separately. But here, yeah, these coefficients depend only on the difference I minus J. And so the function W also only depends on the difference of X minus, of X minus Y. And basically that's then the value that you can see here on this diagonal. So the function is 1 in the black regions and 0 in the white regions. Yeah, and this function W r of x is defined to be 1 if the minimum of x and 1 minus x is less or equal than r, and 0 otherwise. So yeah, as I said, the value on this diagonal here. And now this is an even function, and so we can expand W in terms of a Fourier series, but then because it's an even function, we only have cosine terms and no sine terms, and we denote the prefactors by W hat r of k. So that's a kth Fourier coefficient. Okay, so now in the continuum limit, this is the continuum limit of Kuramoto models on nearest neighbor graphs. And now in this continuum limit, Q-twisted states are given by this formula here. So where theta q is 2 pi qx plus this possible phase shift alpha. So this figure represents a free twisted state with alpha equal to 0. But of course, as I said, alpha could be also pi, for example. Now it seems that this is a discontinuous function, but if you regard this as a function to the unit circle, then it is continuous because there 0 is the same as 2 pi. If you identify 0 with 2 pi, then it's a continuous function. Okay. And now, as I said, you want to calculate the stability, and this continuum limit, calculating the stability is a lot easier. And in fact, that has been done in 2006 by these 3 people here, Wiley, Strogatz, and Girvan. And yeah, they calculated the eigenvalues of the linearization of the right-hand side of this continuum limit here. And they found that they are given by this formula here. So they can be calculated using the Fourier coefficients of the function W. Okay, and so for all integers k, this represents an eigenvalue. Now, if you set k equal to 0, what you find is that this is equal to just w hat r of q plus w hat r of q minus 2w hat r of q. So this will be 0. So yeah, there's a 0 eigenvalue, and this is basically because there's this phase shift parameter. If you perturb the Q-twisted state by a constant function, then you end up with another Q-twisted state that has a different phase shift. So there's this continuum of equilibria, and so this gives you the 0 eigenvalue. Okay, yeah, and since 2006, a lot of work has been done about these twisted states. For example, the stability has analyzed if one reverses the direction of time, and one has also considered twisted states on lattice graphs. Yeah, but our goal was slightly different. So what we did is...
Hey, Tobias, sorry, can you go back?
Yes.
Do you know the multiplicity of the eigenvalue? Like a simple eigenvalue, or it's not simple, but...
I think the multiplicity is always 2. Because...
For eigenvalue, each eigenvalue.
Yes. Yeah, so if... Yeah, the multiplicity is always 2 except for the 0 eigenvalue. The 0 eigenvalue has multiplicity 1.
Simple, yeah.
Because there's only a one-dimensional continuum of equilibria or Q-twisted states. But then you can see if you replace k with minus k, then the eigenvalues agree. So that's why all of these eigenvalues have multiplicity.
I see. Thank you.
Yeah, you're welcome. Okay, so we took that same system, and we wanted to generalize this limit with higher order interactions. So this is the regular continuum limit of the pairwise Kuramoto model on nearest neighbor graphs. Pairwise because there's a pair of oscillators, y and x. These two oscillators interact with each other. And we added some generalization of higher order interactions that are given by this formula here. So here we also have an interaction of 3 oscillators. There's a Z, Y, and X, a triplet of oscillators that interact with each other. And then lambda. Lambda is just a new parameter that is the strength of the triplet interactions. And then we have also added a quadruplet interaction. So here 4 oscillators Z, Y, W, and X interact with each other, and mu is the strength of these quadruplet interactions. Yeah, so in total there are now 3 parameters, R, lambda, and mu. And we summarize those 3 into one main parameter P, and P is now an element from this calligraphic P, which is the parameter space. Now I should also say a few words about why we chose these higher order interactions here, because these higher order interactions do not originate from a phase reduction, but instead we found that these higher order interactions are the ones that are most easily analytically tractable, and so that's why we focus on these higher order interactions, and then our work shows what higher order interactions are in principle capable of.
So Tobias, in which sense is a higher order? What do you mean by higher order?
Oh, sorry. But basically, when I talk about higher order interactions, then I mean everything that is beyond second order. So I consider this as not higher order, but kind of because this is a pairwise, a relation between a pair of oscillators, because you only have Y and X.
I see.
And this is kind of, I would say that this is a higher order interaction,
right?
because more than 2 oscillators interact with each other.
I see. Okay.
So whenever there are more than 2 oscillators, then I refer to this as a higher order interaction.
Thank you.
Or I would also call this here a pairwise interaction, this a triplet interaction, and this a quadruplet interaction. So in this case, triplet and quadruplet are higher order.
Thank you.
Yes, thank you for the question. Okay, so this is the system that we study, or that we want to study. But if we want to look at the stability of twisted states in this system, then it turns out that there's this 0 eigenvalue. The 0 eigenvalue is present because you have this one-dimensional continuum of twisted states. And so you can always perturb the twisted state in the direction of a constant function and end up on a twisted state with a different phase shift. Yeah, so that's why there will be this 0 eigenvalue, and that's kind of annoying or inconvenient if you want to analyze the stability of these twisted states. And therefore, we switch into the system of phase differences. So in the system of phase differences, we define a function psi. Psi is defined to be theta, and then you subtract the value of theta where x is equal to 0. Now you can work it out to calculate the time derivative of this function psi, but that's basically the time derivative of the function theta itself, which is this part for the pairwise interaction, and then you subtract the time derivative of theta where x is equal to 0. This is this part for the pairwise interaction. And then you just also have the parts for the triplet and the quadruplet interaction. But so this is the system that we consider, but you don't need to remember the right-hand side of our system, because we just abbreviate the right-hand side with just an f that depends on the function psi itself and the parameter p. So the function psi then satisfies this differential equation here. And importantly, psi also satisfies this boundary condition. So if you evaluate psi where x is equal to 0, then the value of psi will also be 0. And that's kind of important because then in the system of phase differences, you cannot perturb by a constant function anymore. Okay, so yeah, to summarize that, we now consider this system here, or this differential equation. And in this system of phase differences, a twisted state is now just given by the function 2 pi qx. And now you cannot add a phase shift anymore, because if you did that, you would violate the boundary conditions. Okay, now since we are also interested in the local behavior of the right-hand side f around a twisted state, we also define a function fq. Fq of a function v and p is defined as just the right-hand side evaluated at the twisted state plus the function v, and then you have the parameters. So you can regard v as a perturbation that you add on top of the twisted state. And so v is an element in a function space x, and fq then also maps to the same function space x. And here we chose x to be the space of once weakly differentiable functions, such that the weak derivative is an L2 function. And these functions are also supposed to satisfy the boundary conditions. So at 0, these functions evaluate to 0. Okay, and then in this space x, so x is the space that we want to work with. There you can always, this is kind of a Fourier expansion. You can write each element as this infinite linear combination of elements uk and wk. These elements are the basis functions. uk is just the sine of 2 pi kx, and wk is 1 minus the cosine of 2 pi kx. Usually there would just be a cosine and no 1 minus, but here we also have to satisfy the boundary conditions. That's why there's this 1 minus. Okay. And our goals in this project were to basically study the bifurcation of twisted states and the influence of higher order interactions. So we wanted to know if there exist further equilibria near the twisted states, and if they exist, how we can approximate them, and then what we can say about their stability, and also how higher order interactions influence the stability of these twisted states and possibly the bifurcating equilibria. Okay. Yeah, to start, the eigenvalues are important for bifurcation analysis. So we have also computed the eigenvalues of this function fq. So fq with this index v is the derivative of fq in direction of v, and then we evaluated this derivative on the basis functions uk and wk, and it turns out that the basis functions only get multiplied by one value, c1. So then c1 is the kth eigenvalue of the q-twisted state when the parameters are given by p. And the explicit formulas for c1 is stated here. So you can already remember the first part. So the first part is given by, or is induced by the pairwise interactions. You have already seen this formula. But then now we also have to add this second part. The second part is caused by the higher order interactions, where lambda and mu are the strength of these higher order interactions. And of course, they also have an influence on the eigenvalues. Okay, now to study a bifurcation, we have to make a few assumptions. So we assume that there's a curve through the interior of the parameter space, and we denote this curve by P. And then, we basically say that P has 3 components that are the parameters R, lambda, and mu. So because that makes the problem easier, because now we don't want to study the bifurcation in all 3 parameters simultaneously, but now we only have 1 parameter. This parameter is now called S. And at S equal to 0, we want that one of these eigenvalues is exactly 0. So the bifurcation point should be at S equal to 0. And here we want to say that the Lth eigenvalue is the one that goes through 0. Then we also require that the Lth eigenvalue is an isolated eigenvalue. So this is the only eigenvalue that goes through 0. All the other eigenvalues stay away from 0. And then the 0 eigenvalue should pass through the origin with non-vanishing speed. I think that's also a classical assumption if you want to study a bifurcation. Okay, and then I also want to introduce a bit notation. So we denote N for the null space of the linearization of the right-hand side of this continuum limit. And the null space is then given by UL, so the span, the linear span of UL and WL. You can easily see that when the parameter C1 of where K is equal to L, when this is equal to 0, that just means that the functions UL and WL, they get mapped to 0. So that's why the null space is given by the span of the 2 functions. So this is a 2-dimensional null space, which also explains the multiplicity, that this is 2 in this case. And I also want to introduce the notation X0, which is the trivial complement of the null space in the total space X. Okay, and so now we want to find bifurcating equilibria. And to do that, we have conducted a Lyapunov-Schmidt reduction. So remember, basically, if we want to find bifurcating equilibria, then we need to solve this equation here. So this equation here just means we need to find solution to the right-hand side equal to 0. If we find a solution V here that satisfies this equation, then this is an equilibrium, because right-hand side is equal to 0. So we want to find solutions to this problem. But this is an infinite dimensional problem. V is an element of the function space X that is infinite dimensional. So this problem is a bit hard. But then the Lyapunov-Schmidt reduction tells you that this infinite dimensional problem is equivalent to solving such a problem here, where now you have a function phi that takes a function v and the parameter p and maps it into the null space. So V is an element from the null space, and P is an element from the parameter space. And they are both finite dimensional. N is 2-dimensional, and P, in this case, P is 3-dimensional. And then phi also maps into the null space. So now yeah, phi maps from finite dimensional space into finite dimensional spaces. So this problem is a lot easier to study. And then if you have a solution here to this problem, it means that there's also a corresponding solution to this problem over there. For example, if V is equal to 0, then this will always be a solution, because when V is equal to 0, then this corresponds to the Q-twisted state itself, which is always in equilibria independent of the parameter. And so that's why this function phi evaluated at V equal to 0 will always be 0. And yeah, phi is defined to be in that way. So here Q is the trivial projection of the whole space X onto the null space N. And then you apply it to the function fq evaluated at V plus the function psi of V and P. And then yeah, psi is basically a function that's implicitly to be defined to be a solution of this equation, but that shouldn't be too important now. Important is only that we can now restrict to this finite dimensional problem.
Hi, Tobias, I have a question.
Yes.
Is
Yes.
your linearization of a twisted equilibrium self-adjoint?
Good question. I don't know.
I asked you this question because if I remember correctly, if the intrinsic frequency is 0, the ground model has a Lyapunov function. So linearization must be symmetric. Now you take a continuous limit. I suppose that your linearization is also self-adjoint on your phase space.
Yes,
So
I would also assume so, but
yeah.
I haven't checked.
So automatically your operator is Fredholm, so you can apply Lyapunov Schmidt. That's very good. So you have a very good structure. Yes.
Yeah, okay.
So do you have is your PDE gradient? I mean, is there a Lyapunov function in your model?
I'm not sure. So if you only consider the pairwise interactions, then yes.
If I remember correctly, maybe Shixin Zheng can correct me. If your coupling strength is symmetric, Aij is Aji, then there's the Lyapunov, I think.
Yes, exactly. So that's the condition that you need for the pairwise interactions. You're completely right. But then let me go back to the system.
When you take a limit, I suspect that your equation is also gradient.
Yes. Also for the finite dimensional Kuramoto model, this is then also a gradient system, but I'm not sure about these higher order interactions. So is it still a gradient system if you add these higher order interactions?
Yes.
It could be, but I'm not too sure.
And you find Hall bifurcation. In the end, do you find Hall bifurcation or bifurcation from simple eigenvalues? What do you find? Because if you can find Hall bifurcation, then the system is not gradient.
No, I don't find the Hall bifurcation.
Maybe it's gradient.
Yes, it could be.
Thank you. We can see later. Okay, interesting.
Yes.
Thank you.
So yeah, to summarize this, we now have a function phi that maps from a neighborhood U2 of the null space and it also takes a parameter into the null space. That's both two-dimensional, but maybe a bit inconvenient to work with because n is a general vector space. But what we want to do is we want to have a coordinate version of it. So we introduce some functionals, a functional Z1 star and Z2 star that basically extract the component of UL and WL. So remember that N is the null space which contains all the linear combinations of elements of the functions UL and WL. And so the functional, if you apply the functional Z1 star to a function V in N, then this extracts the component of UL, and Z2 star extracts the component of WL. And then we can define coordinate version phi hat of phi. And we do that by just applying the function phi to all possible linear combinations in N that are then given by A times UL plus B times WL. We apply the function phi to it and then extract the component of UL, and then we do the same and extract the component of WL. And that's how we get a function phi hat that now maps from a neighborhood of R2 into R2. And that makes it a lot easier to work with. And also here we only consider the parameter S. So we directly apply the function phi to this parameter curve P of S. So S is now a value from a neighborhood of 0. Okay, so now we want to find zeros of this function phi hat. And first, we found a lemma that exploits the symmetry of the problem, and we reduced the symmetry to make the problem a bit simpler. So it turns out that this function phi hat takes a vector AB in R2, and then it outputs the same vector AB and only multiplies the length of this vector by some factor. This factor is here given by a function h hat, and h hat is a function which is invariant under rotations. So that means here A phi is the rotational matrix that takes a vector and rotates it by an angle phi. And if you take in vector AB and then rotate it by an angle phi and then apply h hat to it, it is the same as if you directly apply h hat to the vector AB. That basically means rotationally invariant. And so this lemma says that the function phi hat looks somehow as in this figure here. And because h hat is rotationally invariant, a solution that is here, or a zero, which is somewhere here, will produce zeros that are all over this circle here. Because then you can always rotate this vector AB around this circle, and because h is rotationally invariant, all the other points on the circle will also be zeros. And that's quite convenient because it means that if you have a solution or a point where phi hat is equal to 0, so a pair here, then you can construct all the other solutions by just taking this solution and rotating it around the circle. So you can also restrict the search of zeros to just the line where b is equal to 0. So we define a new function, phi hat reduced, that now only depends on a, as this function phi hat, but now where b is equal to 0. So now we only want to find zeros of this function phi hat reduced, so the function with values on this line here. Okay, and so the theorem that we came up with is that we have computed a Taylor expansion of this function phi hat reduced, and the Taylor expansion is given by a times gamma 1 times a squared plus gamma 2 times s, and then some higher order interactions. But if you disregard the higher order terms here, then you can see that this is the normal form of a pitchfork bifurcation when the parameter s goes through the origin. So yeah, we found this theorem last year, but it was only published this year. And the coefficients gamma 1 and gamma 2, they can be calculated from the Fourier coefficients of W. So in fact, gamma 1 can be calculated using this formula here. So where C1 is the eigenvalue, you have already seen a formula for C1, and then all the other coefficients, C2 up to C5, they are also linear combinations of the Fourier coefficients of W. And then gamma 2 is basically the speed with which the critical eigenvalue passes through the origin. Here you can approximate the non-trivial zeros using this formula here. So if you solve this part equal to 0, you find that non-trivial zeros are located at a value that I denote by a app for approximate, which is given by the square root here. Okay, so that's the theory. And now in the remaining part of the talk, I want to apply this theory to a few special cases. So first special case is the pairwise Kuramoto model without any higher order interactions. So here the parameter, basically the only parameter is the coupling range R. We do not have any higher order interactions. So the strength of these higher order interactions is 0. And this figure here shows the eigenvalues. So the coefficient C1 of a 5 twisted state, Q is equal to 5. And yeah, the figure shows how these eigenvalues depend on the only parameter R in the system here. So I have depicted a few eigenvalues, and in particular this orange line here depicts the maximum or the maximal eigenvalue over all k. And when this eigenvalue is positive, of course, then the twisted state is unstable. And yeah, as you can see, it is positive in a large parameter region here. But if you look a bit more closely at this point here, yeah, this is what's also represented in this figure here. Yeah, here you can see that the maximum eigenvalue is in fact negative if R is in between of 0 and this point over here. And the precise value for the parameter where the bifurcation occurs here is r is equal to 0.066. And then if you look even more closely at this point here, that's what's represented in this figure here. As you can see, so this is the eigenvalue, the maximum eigenvalue that goes through 0 here. And if you look closely at this point, then you can see that this maximum eigenvalue is attained by the yellow line, and the yellow line is the eigenvalue where k is equal to 1. So the first eigenvalue is the critical eigenvalue in this case. So L, or in the notation of the theory, the L would be 1. Okay, so to study this, the bifurcation, we then choose a parameter through the interior of this parameter space as the bifurcation point, and then plus s. We want to vary s, and then but we don't have any higher order interactions. And then from the theory, you know that the Taylor expansion of phi hat reduced is approximately equal to this formula here if you neglect the higher order terms. So the non-trivial solutions for A are given by the value A approximate, which is the square root here, as I've told you. And so if you compute this value, you know that phi hat applied to a vector A approximate and 0 is approximately equal to 0 as a value in R2. But then because phi hat is just the coordinate version of phi, you know that phi of A approximate times UL is approximately equal to 0, but now as an element in the null space N. Then what you can do is you can reverse the Lyapunov-Schmidt reduction. So then you know that the function fq evaluated at A approximate times UL plus this function psi at A approximate and UL is approximately equal to 0, but now as an element in X, so in the full function space X. But the point is that the derivative of the function psi with respect to the first argument is equal to 0. And because we only consider the local bifurcation, the value A approximate will be very, very small. And then because the derivative of psi is 0, you can just neglect the function psi here. And this means that fq evaluated at A approximate times UL is approximately equal to 0 as an element in the full function space X. So this would be our non-trivial equilibrium. Or in fact, you can think about this as follows. So you can regard A approximate times UL as a function that you have to add on top of the twisted state, such that the result is again in equilibrium. So here a numerical example for q is equal to 5. I have computed the two values for gamma 1 and gamma 2. Now their value isn't that important, but I would like to point out that both gamma 1 and gamma 2, they are both positive. So, and then if you want to solve this equation here, the square root equation, it means that bifurcating solutions can only exist when S is negative. And so in a numerical simulation, I chose S to be negative, but still very close to 0. So for example, minus 10 to the negative 4. and that gives me a value of A approximate, which is 3 times 10 to the negative 2. And so we can approximate the function v as A approximate times UL, and this is then given by the blue curve here, which is a sinusoidal function with this amplitude here. And starting from this initial condition, I employed a Newton iteration to find the true non-trivial solution or non-trivial equilibrium of the right-hand side FQ, and it turned out that this non-trivial solution is then given by this red line here. So we can see that the blue curve kind of approximates the red curve, and if S approaches 0, then the approximation becomes better and better. And so as I've said, this is just an approximation so the blue curve is an approximation to the red curve, and in fact you can see it as a first order approximation, but we can also derive a second order approximation that's then a little bit closer to the red function. Okay, so now I want to explain a bit how I did this numerical simulation, because the point is you cannot directly simulate the continuum limit, but you can only simulate a finite dimensional model. So you always simulate a finite dimensional Kuramoto model. So remember that this is the finite dimensional Kuramoto model, and the coefficients AL, they are given by this formula here, as I've also put on some of the previous slides. But the problem is that this involves rounding. So you multiply the coupling range R with M, then you consider the biggest integer that is below that, and you have this as your coupling range for the graphs, the finite graphs, the finite nearest neighbor graphs. But the problem with that is that it involves rounding. So you cannot see R as a continuous bifurcation parameter. And in fact, the system, the finite dimensional system doesn't change at all if you vary R by a tiny bit. And so instead of having a nice pitchfork bifurcation, you have a bifurcation diagram that looks exactly like that. So sorry for a hand-drawn sketch, but here you have R on this axis, and then all equilibria are given by these blue lines here. As you can see, this is kind of a step function here, and the width of these steps from here to here, this is exactly 1 over m. So you need to vary R at least 1 over m such that the system changes. And that's also a bit inconvenient for the numerical simulations, because the width of these steps is 1 over m. But if I go back one slide here, S is equal to 10 to the negative 4 or minus 10 to the negative 4. Oops. Which means this difference from S, this is negative 10 to the negative 4. But then the width of these steps is 1 over m. And so ideally you want to make m very, very large, such that there are a lot of steps that fit into this interval here. But S is 10 to the negative 4, but I have simulated the Kuramoto model where when m is equal to 1/1000. So in my example, the width of these steps would actually be 10 times larger than this interval here, which is a bit annoying because then you cannot really find any bifurcating equilibria. And you cannot make m any bigger because then numerical simulations become intractable. And you also cannot make S any bigger because then you have nonlinear effects that kick in. And so a solution that we came up with is that we have replaced these coefficients A, I minus j, with B, I minus j. And the definition of these coefficients is almost exactly the same, but then you only vary one additional coefficient, which means so here for these coefficients, what you do is you suddenly increase the weight of an edge in this graph from 0 to 1, and then you suddenly increase the weight of the next coefficient from 0 to 1. But then here, for these coefficients BL, what you do is you continuously increase the weight from 0 to 1, and so then so that the weight of an edge can also be between 0 and 1. So this is what we do here. And in this case, R is a continuous bifurcation parameter, and then you indeed get this nice pitchfork bifurcation here, and we can compute this non-trivial equilibria on this line here, and this is exactly what I did in the last simulation. Okay, so but let me also say the continuum limit of this system and this system, they are both given by the system that we have considered, but we do not have any theoretical clues for why it should be better to simulate this system instead of this one. Our theory only is only about the limit, not about the finite dimensional system. But I think, or we think it's kind of intuitive to continuously increase the weights of the coefficients. Okay, one more slide about some higher order interactions. So previously we haven't considered these higher order interactions, so now I want to mention what the contributions of these higher order interactions are. So remember that these are the eigenvalues of, so the kth eigenvalue of the q-twisted state when the parameter is given by p. And that's given by this formula here. And this part is the contribution of the higher order interactions, but you can see that this part is independent of k. So if this is not equal to 0, then you can choose lambda or mu big or small enough, and thereby shift all of the eigenvalues uniformly to the left or the right as you want. And these coefficients, or this coefficient here, that's almost never equal to 0 because it's given by this formula here. So basically sinusoidal, which almost never equals to 0. And so you can always choose lambda or mu big or small enough, and thereby shift all of the eigenvalues to be negative, which means you can always stabilize a q-twisted state with these higher order interactions. So for example, this figure here represents the maximum eigenvalue of a Q-twisted state, and how this maximum eigenvalue depends on the parameter R and the triplet interaction strength lambda. In the green regions here, the maximum eigenvalue is negative, and then the twisted state is stable, and in the red regions, the twisted state is unstable. And in this figure, this represents the case where Q is equal to 8. So if you start somewhere here without higher order interactions, then the figure basically shows that if you add enough higher order interactions, you can get into the green region here, where the twisted state is then stable. So by adding these higher order interactions, you can stabilize the twisted states. Okay, and then we can also determine the type of the bifurcation, so whether it's subcritical or supercritical. So we can do that by comparing the stability of the twisted state with parameter regions where bifurcating solutions exist. And yeah, that's how we determine if it's sub or supercritical. And here, if the boundary is given by a blue line, it means that the bifurcation is subcritical. So there, the bifurcating solutions are unstable. But here in the yellow regions, the bifurcating solutions are in fact stable. So this is with just triplet interactions. And one more word about the quadruplet interactions. So as you can see, the influence of triplet and quadruplet interactions on the eigenvalue is exactly the same. So I could have also made this figure with mu here on this axis instead of lambda. And then the colors red and green, they would not have changed. But what will change if you do that is the type of the bifurcation. So here the type of the bifurcation is subcritical, but if you suitably combine triplet and quadruplet interaction, then you can also shift this bifurcation to become supercritical. And not only this, I mean, you can shift all of the other bifurcations to become supercritical, so that you then have stable bifurcating equilibria. So this is what you can achieve with these quadruplet interactions. Okay, that's basically it. I have some conclusions. So my main conclusions are that there exist unstable bifurcating equilibria around twisted states in the Kuromoto model, and then you can use higher order interactions to stabilize these twisted states, and not only the twisted states, but also the bifurcating equilibria. And here are some references. So this is our work where these results have been published. This is the paper where the twisted states have first been studied, and this is the book from which we took the Lyapunov-Schmidt reduction and the bifurcation theory. Okay, yeah, that's it. Thank you very much for the attention.
Thank you very much for this very nice and careful and serious talk. Yeah, I think I have already asked too many questions, so maybe there are some comments, questions from the audience, and even counter examples. Okay? No, kidding. So, comment from the audience, please just unmute your microphone and ask. Any questions? Tobias, can you see us now? See the audience?
Yes, I can.
Okay. Hi.
And maybe I can ask. So I was wondering, when you talk about stabilization of these Q-twisted states, I understand that, I mean, I'm a little bit confused because there were so many equations, but these higher order interactions should modify the shape of the unstable equilibria that bifurcate without higher order interactions, right?
Yes.
So the bifurcating equilibria become stable, but they are not the same that you had without the higher order terms, right?
Yes. So let me go back to this slide. So here at this, so first we have studied this bifurcation here, where the critical eigenvalue is the first one. So if you consider only the pairwise Kuramoto model, then yeah, the first eigenvalue is the critical one. But for example, if R is bigger, let's say R is 0.3, then the maximum eigenvalue is, I think here it's the fifth eigenvalue, k is equal to 5. And
Yes.
then instead of having, so this is the function u1 for the pairwise Kuramoto model, but then in order to get the bifurcating equilibria, you would then need a function u5, so a function which has 5 periods in this interval. So 5,
Yes.
yeah,
5 zeros.
That's how the profile looks at a bifurcation here at this point where R is 0.3.
Yes. Yes, but my question was, if you have, perhaps I rephrase. Okay, so you have a bifurcating equilibrium, right, from the original equation without higher order terms.
Without higher order, yeah, okay.
But the issue is that this is unstable, right? Like this is k equals 1, I think, or yes.
Wait, sorry, what is unstable?
Yes, so the bifurcating equilibrium is
Yes.
unstable. Like you have a
Yes.
subcritical bifurcation.
Yes.
And then your claim is that introducing higher order terms, you can make it stable.
Yes.
But my question is, the new thing that you obtain, is the new thing that you obtain the same thing that you had without the control term? Or is the control term modifying the shape of the bifurcating equilibrium? This was unclear to me.
No. It depends. So here at these blue regions, of course, the bifurcating equilibrium is a different one than in the yellow regions here. Because here the maximum eigenvalue could be attained, as I said, maybe by the fifth eigenvalue, or by the fourth eigenvalue, or by any eigenvalue. But then if you lower R and consider maybe this bifurcation here, and here for small values of R, yeah, the bifurcation, the critical eigenvalue is the first eigenvalue.
I see.
And so at this values here, yeah, the profile will look as in this figure here, but not necessarily over there.
I see. And then in this transition from yellow to blue in the boundary, something must happen, right? Some sort of secondary bifurcation nearby.
Yes, yeah, exactly. That a bifurcation turns around. But I haven't looked at this bifurcation in detail. So
it would be
there
nice
must,
to know.
Yes. So there must be a line through the parameter space somewhere here that goes through this point, and then basically divides this region into four separate regions. Oh yeah, I could analyze this numerically or theoretically, but yeah, it's interesting, but I haven't done it yet.
There should
You
be
have to
some
stop
kind
at
of
some
bifurcation.
point.
This may be zero pitchfork bifurcation, zero pitchfork, simple pitchfork. Yeah, higher degeneracy. Yeah.
Yeah.
Sorry, can you repeat?
Thank you.
No, I am just thinking this kind of bifurcation should be already being recorded in the literature. Yeah.
Yes, yeah.
That's yeah.
Yes, you're right. And there's also a paper by my two PhD supervisors about this phenomenon, how you can turn a pitchfork bifurcation around. It's called a universal route to explosive dynamics, something like that.
Okay, good. Good. Any other comments, questions? Maybe let me ask a question, because now in this slide you have a formula for your I would call principal eigenvalue curve C1.
Yep.
And surprisingly to me that you have a triple interaction and a quaternion interaction, but in the eigenvalue level they have a same effect, right? They have a 4 lambda plus 2 mu. So
Yes.
this
Yes.
this high order perturbation, there's a triple, there's a quaternion, but they have the same effect to the eigenvalue.
Yep.
But I think they should have a different effect somewhere, and where are they?
So you can also do the same with
So my idea is maybe when you do tighter expansion of your Lyapunov-Schmidt reduced equation, and this higher order perturbation will give you different formula of your coefficient of your tighter expansion. Is that true? Or
yes, yeah. So you can see that C1, the effect of lambda and mu on this C1 is almost exactly the same.
yes,
Then if you consider this formula here,
yes,
then the effect of lambda and mu on these other coefficients here, this is not the same anymore.
I see.
And this is how you can turn the bifurcation around, change it from super to subcritical.
So the triple interaction is not enough to twist the bifurcation. Only triple and quaternion both.
If you want to turn the bifurcation around, so change the type of the bifurcation, then yes.
Interesting. Triple is not enough.
It could be that you add a second type of triplet interaction. Maybe that's also sufficient.
And do you know why? Just by calculation, or there's some symmetry argument?
So here in the system, so this is the triplet interaction that we have studied.
Yes.
But you could also consider the triplet interaction, which is theta of x plus theta of y minus 2 theta of z.
Yes.
That's a fundamentally different triplet higher order interaction. And maybe that is also sufficient to turn the bifurcation around. I would have to do the calculations if it indeed works, but
I see. Okay, thank you. Yeah.
Yeah, you're welcome.
So, other questions? So if this is not the case, then let's thank our speaker Tobias Böhle again.
Yeah,
Thank you. Yes.